Hello all, these are the worked solutions to group work B7. So the first question is about a beautiful American eagle, which I can only assume is meant to be a bald eagle. So my little bald eagle over here, I'm very sorry, I drew the mouse in its talons, but the problem says that it was in its beak. So I hope you can forgive that oversight. But here we go. The eagle is traveling with a speed of 2.7 meters per second, which means the mouse is also traveling at that speed. But then it lets go of the mouse, which means that the mouse is going to stay moving in that direction. So it keeps its velocity of 2.7 meters per second in the x direction until something causes it to change. That's what Newton said, so we're going to go with the number 2.70 as the velocity in the x direction, because that's the initial velocity. Now its initial y velocity is that it's being dropped from a height, so it has this velocity. Over here you can see like the velocity is the same at every instant in the horizontal direction, but vertically, as time passes, the velocity begins to increase. Here's little, medium, big. So the longer that it falls for, the faster its vertical velocity will become. And so of all the things that you know, the question is it lands on the beach 2.1 seconds later. So you know that its initial velocity in the y direction is 0. We don't really know the height that it was dropped from. We could later figure it out, but it doesn't tell us in the problem, so that's unknown. This is, I decided to set the bottom of like the beach. I decided to set that at 0 meters. We know the acceleration of gravity is in the y direction in this case, and so that's negative 9.8 meters per second squared. And it does tell us that the time that it falls for is 2.10 seconds. So if the question is what is its final velocity in the y direction, that's the vertical component. The velocity in the y direction, I'll just add a little subscript here. The velocity in the y direction is equal to the acceleration in the y direction times the time plus the initial velocity in the y direction. So that one was already 0, so we don't even need a term for that one. And acceleration of gravity times the time gives us a final velocity in the vertical direction of 20.6 meters per second. Now, if the bird flies faster, if he's flying faster, in this case, because he's dropped at a horizontal motion, whatever the initial velocity is, that's going to be the velocity of the x direction. So if this goes up, that's going to go up. Now, in the vertical direction, though, the horizontal and vertical are independent. They don't affect each other. So if this goes up, this doesn't change. The only thing that affects what the final velocity would be is the height that it falls from, because this displacement, which we don't actually know, but if that's the same, the time is always going to be the same because gravity accelerates at a constant rate. So even if the eagle is flying faster, its final vertical component will not be any different, though its horizontal component does increase. Okay, question 2 is about a rope swing. So this kid's on a swing, and he's going to go over the swimming hole, so he swings from the tree. So he lets go of the rope, and at that instant, the instant he lets go of the rope, he has a velocity of 2.25 meters per second at this angle above the horizontal. So whether the horizontal is down here or if you make a parallel line up here, it's going to be 35 degrees. So if you projected that backwards, this angle would be 35 degrees. So it tells us the time that he's in the flight for, so I noted that here, and acceleration of gravity is going to be useful here, so I reminded us that's it. And the question is, how high above the water was he when he let go of the rope? So that's really what you're trying to solve for, is the displacement. How far does he move from where he let go of the rope to when he landed? So his path would have continued in this way and then eventually would have fallen, but because he has this initial velocity at that angle, we can now determine the two components. Here they are. So you know the initial, you know that the vertical component is just the sine of this angle is the vertical divided by the actual velocity. And the horizontal component divided by the initial velocity is equal to the cosine of this angle. So I solved for each of those down here. So the horizontal component is 1.84 meters per second, and the vertical component is 1.29. Remember, you can check to make sure this works if you want to use the Pythagorean theorem in reverse. I did already, so it's good to go. So we can look at each dimension, and since we're talking about the movement in the y direction, this is displacement in the y direction, and this is just the displacement of the y. So those two things mean the same thing. But in this case, we have 1/2 at squared plus the initial velocity in the y times the time. And so these are the things that we knew from the problem and the thing that we solved with our trig. So now that you have all of the terms you need in order to solve for the delta y, you plug them into your calculator and you determine that the final change in position is 1.06 meters down. So your answer could actually just be 1.06 meters. It doesn't have to include the negative. If you were to include, if the question was like, what is the displacement of the young kid, then you would have to put the negative value because displacement is a vector and vectors need direction and magnitude. Oh yeah. Okay, question 3 is about a soccer player. So when you kick a soccer ball, it follows this parabolic trajectory. And here's the situation that we have to begin with. You got a soccer player who's going to kick a ball. And it says that the speed at the beginning is 10.2 meters per second. And it even tells us this direction, 25 degrees. So that means you can determine the velocity. So the magnitude of the velocity actually is 10.2 meters per second at 25 degrees. That would be the term velocity, the initial velocity. But if you're going to look for its two components, after you're being kicked, you need to know how do the x and y components change at some time in the future. So the horizontal component and the vertical component are based on the initial velocity at this angle. So the sine of 25 is the vertical component divided by the initial. So that'll be 4.31. And the horizontal component is the cosine of this angle is equal to the horizontal divided by the initial. So that gives you a 9.24. And so at 0.25 seconds, the vertical component changes, but the horizontal component does not. This one stays at 9.24 the entire time because we are ignoring the effect of air resistance, or we're assuming that is insignificant. So if we zoom in to look at what's happening to the velocity in the y direction, that is the one that changes. Oh, this should say v naught y. That's where it changes. V naught y. All right, now at a certain instant, you can determine its velocity if you know the acceleration, the time, and the initial velocity. And this is where the sign starts to really matter because the acceleration is down, but the initial velocity was up. So if you substitute, solve, you get an initial velocity, you get a velocity in the y direction at 0.25 seconds is 1.86 meters per second. So at 0.25 seconds, when you substitute that in for t, this is the velocity that you would get in the y direction, which maybe you'll notice that's less than it was at the beginning. And that should make sense because this ball is accelerating in the downward direction. So if you started moving up, as it accelerates in the downward direction, the number becomes smaller. So that's fine. We have the final velocity at 0.25 seconds. But we also need to report its direction. So in this case, now here's the ball. We don't know what this value is, but the x dimension doesn't change. It's still that dimension. It's still 9.24, I think. And the y is now this new number, 1.86. So to determine the resultant vector between these two components, you use Pythagorean theorem. So The resultant vector is 9.42 meters per second, which is less than it started with, and that should make sense. Like, as a ball is flying, it actually does slow down a little bit because it has a horizontal and vertical component, and the vertical component is reducing. So now that you know the final velocity, you could use either one, trig. You could use any of the trig functions, but I decided to use the sine of this angle is the vertical component divided by the resultant velocity to get an angle of 11.4 degrees. So to answer the final question, you would say that the velocity at 0.25 seconds is 9.42 meters per second at 11.4 degrees above the horizon. The next question is basically the same question, just at a different time. What is the velocity at half a second after it's kicked? So you could end up solving for it. Now this one, if you compare it to the one before, is a little slower, but is it slower because it's before or after its height? So you can figure out at half a second, the velocity is negative 0.59 at this point. So the Pythagorean theorem, again, to the rescue, produces your new final velocity of 9.26 meters per second. And then when you do your trig, the opposite side of negative 0.59 divided by, I guess in this one I showed that you can use the tangent. So the opposite over the adjacent is 0.59 divided by 9.24 and gives you an angle of gives you an angle of 3.63 degrees. So to answer this question, you would say that the velocity at half a second after being kicked is 9.26 meters per second at 3.63 degrees below the horizon. Because in this case, your vertical component of the velocity is downward, which indicates that you must have already passed the maximum height. Because the direction of the y velocity has changed, we're past. So if we look back at the trajectory of the ball, we're about like right here. We're somewhere just past the peak, because at this case the velocity in the y direction has become negative. All right, the last question from this problem set imagines you and a friend standing on a roof, and you each have a snowball, and you throw them with the same speed, but one goes up and one goes down. So if this is you and you throw yours straight down, your velocity graph would look like this. The initial velocity is negative because it's towards the ground, and then it accelerates after it leaves your hand. So the velocity does change, and the way it changes is due to the acceleration of gravity. Now your friend, if she has a snowball and she throws it up like this, so she throws hers up, now that means that her velocity at the beginning was positive because it was going up, but it also accelerates after it leaves her hand. And so like at the same point on the parabola, so like at the same position, you would end up with the velocity at the same point. I know it's hard to imagine this without any values, but the calculation that is used to illustrate this is that the velocity in the y direction, v naught y, v naught y, they have to be the same because the angle is the same. The angle is both 40 degrees. It's just that one is up and one is down, and in the equation that we use to illustrate the final velocity at the end, the change in position is the same. It starts here and ends here. We don't need to calculate the distance that the snowball travels, we need to calculate the change in position. The acceleration due to gravity is the same. And so this is the one that can be different, but if one is a positive number and one is a negative number, when you square it, you end up with the positive version. So it doesn't matter whether you throw it up or down, when the snowballs land on the ground, the speeds will be the same. That's it. If you have questions about this problem set, feel free to come see me or your teacher. Good luck studying for your tests and quizzes.